Thank you everyone for joining and welcome to another episode of the C2QA Colloquium, I believe the last one of this academic year. I'm really excited to introduce today's speaker to you. This is Ansejo Garcia. Ana graduated from the Universidad Complutense de Madrid in 2014. She briefly joined the Institute of Photonic Sciences in Barcelona as a postdoc before she moved on to Caltech, where she held a postdoctoral fellowship at the Institute for Quantum Information and Matter. And she also later received the prestigious Marie Curie Fellowship. Ana joined Columbia as an assistant professor of physics in 2019. Her research focuses on theoretical quantum optics and its intersection with quantum information and condensed matter physics. She's been awarded a large number of very important prizes and awards. It's quite amazing. She received the Packard Fellowship, the NSF Career Award, the AFOSR Young Investigator Prize, and the Sloan Fellowship. And then the most recent, I believe, of all these honors is the Early Career Scientist Prize in AMO, awarded to Ana this year by the International Union of Pure and Applied Physics. And I quote, "For her outstanding theory contributions to the understanding of fundamental physics associated with light-matter interactions in cold and ultra-cold atoms, the role of many-body optical phenomena and their applications to quantum technologies." So Ana, I'm really happy that you could make it, and I'm very much looking forward to your talk. The floor is all yours.
Thank you so much, Jens, for this very kind introduction and also for the invitation to talk here about our work. So let me share a screen on my talk. So hopefully you can see my talk. I should say that if you have any question, you feel free to interrupt me. I'm happy to take questions during my talk. Okay, so today I'm going to be talking about quantum many-body physics with atoms and photons. And so we all know that the many-body problem, where we have many quantum particles interacting with each other, is a hard problem. And this is because interactions in complex systems give rise to emergent phenomena that cannot be easily predicted from the underlying microscopic particles. So in the classical domain, an example is that of an avalanche, where we have some complex behavior that cannot be understood from the study of the structure of a snowflake. In biology, we perhaps know that when many fireflies get together, they synchronize. So this behavior of, this collective behavior cannot be understood from the deep study of the biology of a single firefly. And so today I'm going to talk about a many-body problem in quantum optics that is called Dicke superradiance, where photon-mediated interactions between atoms gives rise to a synchronization of the atomic dipoles and to an avalanche of photons. And I am interested in this problem because it's here, it is dissipation what creates correlation between the atoms and entanglement between the atoms, and as well as also a macroscopic and robust behavior of the atomic ensemble. And so the big question here is, how do we bridge the gap between the microscopic degrees of freedom, this is a single atom interacting with light, and the macroscopic behavior of the ensemble? And so again, this is a problem that is generically hard in an extended system, but we have found a way in order arrays. So if you look at the history of the field of quantum optics and light matter interaction, I think there are like two main platforms. One is cavity QED, where you have a single atom or perhaps a few interacting with a single optical mode. So in this situation, we have a very high degree of control, but what my claim would be that also we have very little complexity in the physics. On the other hand, people have been doing experiments with dense clouds of atoms. So here we have many degrees of freedom. So we have many atoms, we can have many excitations, And also you have many optical modes that are that of the free space, electromagnetic field in free space. And so this here is a system where you have a lot of complexity, and it's very hard to describe actually, but there is very little control. And atomic arrays, on the other hand, bring the best of both worlds together. They provide a degree of control because there is a notion of order in the system, as we have effectively a crystal of atoms, but also they allow for very rich and complex behavior. And so you may be familiar with all the work on Rydberg atomic arrays for quantum simulation of Hamiltonian spin models. But today I'm going to be talking about something different, that is indeed many-body physics, but not of Hamiltonian systems, but instead in open, which is dissipative quantum systems. So where you have truly like radiation of light and loss of excitations. So a very big part of my work is motivated by the recent experimental advances in creating ordered arrays of emitters. So this does not only include atoms, but also there are a lot of work in solid state emitters. So let me just review a few of these works. So I wanted to show you some works in creating ordered arrays with optical tweezers. So here every point is fluorescence of a single atom. And so you can trap them with an optical tweezer that is basically some light field. And then these optical tweezers, if they are filled, they can be rearranged, and then you create a very beautiful ordered structure. This can be done in 1D, it can be done in 2D. And if you're creative, you can also create the landmarks of your city. So this is the group of Hannes Bernian in Chicago, and this is the group of Antoine Brouwys in Paris, where they created the Eiffel Tower in 3D. So besides this, there has also been a lot of work in solid state emitters. So this is an example where they create emitters by placing a 2D material on top of silicon nanopillars. So this creates a confinement of the excitation, so effectively a quantum dot, and this produces emission of light. And many of the a lot of the work that we do can be extended not to just atoms or solid state emitters, but to superconducting qubits in, for instance, the microwave regime. So here this is an example of a bunch of superconducting qubits coupled to each other via transmission line. So this is what I showed you before, are examples of people actually building up these ordered arrays, but there has been also recent developments in interfacing these ordered structures with light. So I wanted to discuss a couple of experiments. The first one is this experiment here. So this is an experiment in the group of Immanuel Bloch in Munich, where they place a layer of atoms in an optical lattice. And the distance between these atoms is smaller than the wavelength of the light that they are sending. So then when light impinges on this like single layer of atoms, in theory, it can be perfectly reflected because a 2D array of atoms behaves as a perfect mirror. This is in theory. So if you do the experiment, the reflectance is 60%. But actually last week I was in DAMOP and Immanuel gave a talk, and he mentioned that he would expect this to go higher, probably above 90% by tuning some parameters in the experiment. Another related experiment is also published, an experiment published in the same year, is that by the group of Antoine Brouwys. Sorry. Okay, so here we have an array of atoms, even though we're not seeing them, like we see just a continuous line. And so what they see is they send light, and basically they can probe frequency shifts that the atoms experience based on the interactions with their neighbors. Okay, so people are getting there now experimentally, creating arrays of sub-wavelength distances and interfacing them with light and seeing this collective behavior. On the other hand, both two of these experiments have been performed in what I would call the single excitation regime, which is we have an atom excited We don't know which one, so it's in a superposition, right? Where all the atoms are in the ground state except for one. And so this effectively is like classical behavior. So if you would remove the atoms and place antennas or metallic nanoparticles, you will see exactly the same. You send light, and if the particles are placed at a distance smaller than the wavelength, you will see the light coming back. And so I want to go beyond this, perhaps one could call more classical regime, and start packing up more excitations and more photons in the system. And then try to answer the question of what is the many-body physics of these systems where you have many excitations. But of course, the problem in that case becomes a many-body problem where we not only have many atoms, but also many excitations. And this problem is generically very hard to solve. And so this brings me to the notion of Dicke superradiance. So this is the first many-body problem in quantum optics. So this is a problem that was actually first studied by Dicke in 1954. And so what Dicke realized is that if you have a bunch of atoms or molecules or generically any emitter that behaves, that responds to light, if the atoms are really far away from each other, when they are excited, they will decay without seeing the neighbors, and they would decay at a rate, they would emit photons at a rate that decreases exponentially with time. So this will be like this type of plot here on the right. So this is taken from a very famous physics report paper by Gross and Harrows. Okay, so now what if you put all of them together? So if you put all of them together, what you should see in the photon emission rate versus time is a rapid increase and then a decrease. So this is what is called the superradiant burst. Basically, all atoms synchronize and decide together to release most of the energy at a given time. And so superradiance is an example of the emergence of macroscopic coherence through dissipation. You start in a state, or the system starts in a state that has no coherence, no correlations. Is effectively a product state where all atoms are excited. Due to vacuum fluctuations, the atoms start decaying. And through this decay, they start establishing correlations that lead to desynchronization and to the emission of light in a burst. Okay, so let me explain to you Dicke superradiance in a cavity, and then we're going to take this knowledge and go to extended systems. So Dicke superradiance in a cavity is basically the following. We have a bunch of atoms between two mirrors. As I mentioned before, the initial state is uncorrelated. So if I plot the states that are relevant in the dynamics, I will have the initial state that is a product of all atoms excited that has n excitations. And then all the atoms talk to a single optical mode, that is the cavity mode. And so this imposes a symmetry in the problem, that is that all the atoms talk to each other at the same rate. So this means that when the atoms emit a photon, the only possible states that this emission of a photon can produce are states that are permutationally symmetric, because you cannot distinguish one atom from the next. So if you look at the state that has been generated as after the emission of a photon, you have a hole, so an atom in the ground state, but you don't know if it's in the first atom, the second atom, or the nth atom. And then you do that again, and then you have two holes, but then again they are distributed in this way where you have like this coherent superposition, all with pluses. And so basically these superpositions make the emission of a photon more likely. And so this produces this acceleration of the emission of photons. And so the beauty of this Dicke model is that here the complexity is reduced because of the symmetry, and it's exactly solvable. And so you can think of the process of Dicke superradiance effectively as a photon avalanche. So basically we have a quantum fluctuation that here would play the role of a skier that produces a very rapid release of photons, which here is the snow basically. And very importantly, all these photons are emitted into a single decay channel, that is the cavity mode. So here the fact that you have one mountain ridge instead of 25 really, really matters. The fact that you really have the mirrors that constrains the number of decay channels that the system has. And so as we will see, this is not the case in extended systems. So, okay, I think I have established, or actually Dicky established many years ago, that many atoms radiate differently, not just more. And so this is not just a theorist's dream. This has been observed in multiple systems. So besides atoms in free space and atoms in cavity, it has been observed in perhaps more exotic systems, such as Bose-Einstein condensates in an experiment of the group of Wolfgang Ketterle at MIT. And also it has not only been observed with atoms, but also with other types of emitters, like, for instance, with perovskites. And so another thing that I wanted to highlight is that superradiance is also not just fascinating from the point of view of a theorist, but it can also be used for applications. So you can come up with ideas like the superradiant laser, which is a laser that works in the band cavity limit, where the coherence of the laser is actually stored in the atoms. And this laser is very stable against thermal fluctuations of the mirrors. And so you could say, well, if this problem has been solved in 1954 by Dicky, why am I even here? And the answer is that Dicky solved this problem in a cavity, where again, there is a high degree of symmetry. And there is a decades-old question that is what happens in extended systems. And this has been debated for a very long time. And so as an example, I wanted to highlight again this paper, the review paper of 1992. There is a section of it where they discuss potential geometries that would preserve Dicky superradiance. And what they were thinking back in the 80s is that there is an issue when you make systems extended, that is what they call the dipole-dipole interaction. So as I will describe later, the fact that we are in free space switches on a coherent interaction of the type of 1/r³. And they thought that this would dephase the system. And they are thinking, well, what type of geometries can we make such that they preserve some sort of permutation symmetry that would be perhaps more robust to this dephasing? And so they came up with the idea of rings. Rings perhaps are more robust to this issue. And so we'll see about that, because we actually have results on rings and how well they perform. Okay, so this is basically the type of problem that I'm gonna be talking about. So what happens for Dicky superradiance in extended systems where you don't have symmetry, or at least you don't have like permutation symmetry? So the first thing that I wanted to highlight or comment is, well, we can make a wild guess, or actually an educated guess. That is, imagine that we're going to plot the photon emission rate versus time for different types of systems. So I take an ordered chain and I ask myself, am I going to have Dicky superradiance if the distance between the atoms is very, very large? And the answer is obviously not, because we should have a monotonic decay, because if the distance is very large, the field in free space decays with distance. Therefore, atoms should not see each other. Therefore, we should have like boring decay. On the other hand, if we go to the other extreme limit, if we place all the atoms, at least in theory, in exactly the same point, they talk to each other at the same rate. Therefore, we should go back to the limit of Dicky, where we have a peak emission, the maximum of emission at the time that is not zero. And so this leads to a superradiant burst. And the question is what happens in between these two regimes that we know the answers for. And the problem is that if we try to calculate the full dynamics and solve the question, it's exponentially hard. So we cannot do that in a computer. And so what I'm going to do now is I'm going to build intuition and also a bit of the theoretical framework that we use to deal with this problem. So before I go to the problem of many atoms, let me discuss a single atom. So I'm going to consider a single atom as a two-level system where I have an excited state and a ground state. And I'm going to monitor the population of the atom in the excited state. So here is a plot of the excited state population versus time. So my atom is going to be in the excited state for a while until a moment where, stochastically at a random time, it emits a photon that gets detected. And then I know that it is in the ground state. And this jump from the excited to the ground state, theoretically, we describe it in terms of what is called a jump operator. This is a sigma minus type of operator that brings you to from the excited to the ground state. So if I do this again, and I repeat my experiment. I place my atom again in the excited state and I monitor it. This emission will occur at or this projection to the ground state will occur at a different time. And this again, because it's a stochastic process, and it's a stochastic process because when the atom is in the excited state, there is no coherence. So the only way that it decays is because of vacuum fluctuations. So vacuum fluctuations obviously means that this is stochastic. And so if I do this again, now I will detect the photon at another time. And if I continue doing this, then I end up with a description of the problem that is statistical, that would correspond to a density matrix approach, where the atom goes from the excited to the ground state at a rate, following this exponential, at a rate that is the spontaneous emission rate that is determined by the environment. So in vacuum, it would be that of vacuum. And so one other thing that I should mention is that this emission not only occurs at a random point in time, it also, the photon is detected in a random direction. And when I do this experiment many, many times, I will recover the typical dipole pattern. Okay, so this is the notion of a quantum jump for a single atom. And so now I'm going to look at many atoms. So the many body problem, this problem is a many body because we have many atoms. So we have a Hilbert space that scales as 2 to the n, where n is the atom number. And then we have many electromagnetic modes. In free space, we have infinite of them. So the problem becomes very hard to treat. So the first thing that one can do is to treat the field, the electromagnetic modes, as an environment, as a path, and we can trace out that. And so in the end, we end up with an open quantum system with long-range interactions. Part of them are coherent and part of them are dissipative. And so when we do that, we find an equation, a master equation for the density matrix, which is the density matrix that only has into account the degrees of freedom of the atoms, that has two different parts. The first one is a Hamiltonian evolution. Here, this is what is called the coherent evolution. It conserves the number of excitations in the system. On the other hand, on the right, we have the Lindbladian. So this emerges whenever we have an open system. And here we do have an open system because, again, we have traced out the electromagnetic degrees of freedom. So we lose information about that, which means that now we have a path. And so here, this part that is the Lindbladian accounts for this dissipation, and the dissipation, as you see, is not local in atom label. So, but we have instead something that depends on atom I and atom J. So they decay collectively, they emit photons collectively. And the rate of this photon emission is given by the imaginary part of the propagator of the field in free space. So this is where we build the geometry. So if we have a disordered cloud, we will have the different positions, and then we can calculate the propagator, and we will build this matrix, basically these coefficients. And if we have an order array in 1D, it will be one thing, or an order array in 2D, it will be another. And so, because this is the part that I'm most interested in, because I'm interested in emission of photons, I'm going to be focusing on this part here, okay? And so let me tell you what happens when we place the atoms in a cavity and then free space. So in a cavity, these rates basically are the same for every pair of atoms because of the mirrors. So it doesn't matter the distance between the atoms, the rate at which they talk is the same. So again, the symmetry makes the problem of Dickey superradiance exactly solvable. If we go to free space, as I mentioned, now atom 1 talks to atom 2, different from atom 3 and different from atom 4 because the field decays in free space. And now the interactions depend on the interatomic distance and the symmetry is broken. So let's try to treat this problem in a different basis, try to look at it in a different basis, that is the collective basis. So I'm going to take this Lindbladian, and I'm going to take this matrix gamma ij, which has, it's an n by n element matrix, and I'm going to diagonalize it, okay? So now you see that this is written in terms of collective jump operators, which are these O's. So they are the same operators as we have for a single atom. It's a sigma minus operator that brings the atom from the excited to the ground, but now it's collective. So we don't know which atom is emitting the photon. Therefore, we have a superposition that is labeled by alpha. And so this is an eigenvector of this gamma matrix. And each of these jump operators represent the emission of a photon. Because it is collective, the emission of a photon produces a set of phases, dipole phases on the atoms. And it also produces a photon which has a very specific far field profile. And because it's an n by n matrix, we have n of these jump operators. And each of them may have a different rate of action, which is given by gamma nu. So these are the decay rates. These mean that if gamma nu is very large compared to the spontaneous emission rate of an atom in free space, it means that this jump operator is very super radiant or bright. So it acts very frequently. So you emit photons very rapidly via this decay channel. On the other hand, if this gamma is very little compared to gamma 0, this means that this operator is dark, is very unlikely to act. And if it would act, it would mean like it will take you a lot of time to get the photons out via this decay channel. Okay. Okay, so then if we have this density matrix now, this master equation, now we can calculate the any observable, in particular the emission rate, the photon emission rate for different geometries. And this is what we did numerically first to see, what happens. And the answer is here. So this is the exact dynamics. This is the normalized photon emission rate versus time in free space for arrays with a lattice constant that is 0.1 the wavelength of the transition. And so you have here different geometries, a chain, a ring, and a 2D array. And the first thing that we realize is that dimensionality really matters for Dickey superradiance. So 2D arrays seem to be doing much better than 1D arrays. And remarkably, perhaps in contrast to what was thought in some of the literature, chains and rings perform effectively very similarly. So this is the first thing that you learn, dimensionality matters. The second thing that you learn is that this is a very, very depressing result. And why this is the case is because I have plotted this very beautiful 2D array here, but in reality, these calculations are for 16 atoms. So this is actually a 4x4 array, and there is no computer in the world that can solve the dynamics of a 5x5 array. So it's really sad. And for a 3D array, we could only do 2x2x2. Again, we cannot do 3x3x3. So to try to get intuition or understanding the physics of many-body decay from just numerics seems, overall a pretty bad decision because you can do very limited sizes. So luckily for us, this is not all that we can do. We can start to think about it in a perhaps more detective way, like what is leading this behavior. And so the first thing that we did is we took this master equation and we removed the Hamiltonian part, the coherent evolution. And what you see is that if you remove the Hamiltonian, basically the dynamics looks very similar, okay? And in particular, the early part of the dynamics is almost identical. So the first hint that we have is that the Hamiltonian does not seem to be doing much. The dynamics is mostly dissipative, which means that it's driven by the jumps, by the process of photon emission. This perhaps is not surprising because this is a process of an avalanche of photons. So it makes sense that the dominant part of the dynamics is the dissipative part. The second thing that we did was we looked at what happens with the burst as we make a chain, for instance, go from all the atoms in one point and we stretch it slowly and we make it longer. So you see here when all the atoms are in a point, we get the decay result. When we stretch it such that the distance is now 0.1 lambda, the burst decreases. And if we stretch it too much, then the burst completely disappears. So it's clear that the superradiant burst is lost, at least in 1D, for very large interatomic separations. And so once we looked at this plot, we realized something else, is that we can predict the burst, whether the burst is going to happen or not, just looking at the slope of the curves at t equals 0. We cannot say how big it is, but we can say whether it is going to be there or not. So the answer for at least try to understand the origin of Dickey superradiance might be to just look at the derivative of this curve at 0 time. So because this is again an avalanche, the atoms either synchronize in the beginning or they do not synchronize. Therefore, just looking at whether the initial conditions are good enough for this avalanche to occur is a good predictor for decay superradiance. And so what we came up with is the notion of a minimum burst. So here, the minimum burst is that the first photon, the emission of the first photon, enhances the emission of the second. So emitting a photon creates correlations in between the atoms that makes the emission of the second more probable. So we can write this in terms of a second order correlation function where we have that the probability of emitting 2 photons divided by the probability square of emitting 1 photon is larger than 1. And we can compute this in terms of our decay rates and jump operators. And you can do this actually in like a page. And the solution for whether this condition is fulfilled or not reduces to this answer. So here we see that the condition for a minimum burst is that the variance of the set of the decay rates properly normalized is larger than 1. So I really like this equation because of two reasons. The first one is that it provides a lot of insight into the origins of decay superradiance. So in decay superradiance, or what matters is how many decay channels do you have in your problem and how different they are. So to have robust decay superradiance, you need dominant decay channels, and you want some others that are irrelevant, okay? And so this is precisely what happens in a cavity where you have only one dominant decay channel, that is the cavity mode, and all the others are effectively suppressed. In free space, as we will see, there are ways to make some channels dominant versus others, and they rely on interference. The second reason that I like this equation is that we have to obtain a variance of a set of eigenvalues of an n by n matrix. So this can be done with a complexity that scales linearly with atom number. And so now we can bypass the difficulty of evolving a differential equation in an exponentially large Hilbert space. So it means that now we can take this equation and use it as a predictor of decay superradiance for very large systems of atoms. And so one thing that some other insight that I can provide with respect to this equation is the following. So decay superradiance occurs because of this successive photon emission. But then in free space, these photons can be emitted towards you. They can be emitted towards me, towards the right, towards the left, bottom, top, in all directions, right? So if we make it such that our array mostly decays into some channel, only one, then this process of photon emission is imprinting always the same phase on the array and refacing the array and imprinting very strong correlations. So this leads to decay superradiance. On the other hand, if one photon is emitted in one direction, the next one in another, the next one in another, what this produces like a different set of phases every time, and this effectively dephases the array. So dissipation either gives you decay superradiance or quenches decay superradiance. It can go both ways. And so in free space, the number of radiative decay channels, or the ones that are relevant, is determined by two things. The first one is dimensionality, so whether you have a 1D, 2D, or 3D array, and the second is the lattice constant. And if we want to maximize the variance to make these channels very different from each other, we have to rely on constructive interference to make some channels very dominant or bright, and also destructive interference to switch off some channels. And so in a cavity, we do that by modifying the boundary conditions. We place mirrors here, and so that determines one mountain ridge, okay, in this notion of avalanche. Here, these mountain ridges in free space are emergent, and they emerge through interference. And so if we have this equation, now we can define a critical distance beyond which superradiance is lost, because interference is not going to be strong enough to sustain either very strong constructive or destructive processes. Okay, so just to prove that this notion of variance or second order correlation is a good figure of merit for predicting superradiance, here are some exact results where we plot the time of peak emission rate, Tmax, versus the second order correlation function. So below 1, we have not a burst because the peak of the time of maximum emission is 0. So we have this monotonic decay. As soon as we cross 1, then the peak of maximum emission deviates from 0, which means we have superradiance, and therefore the second order correlation function is a good predictor for this physics. Okay, and so the last ingredient is I want to explain why the interatomic spacing matters and why it controls the number of radiative decay channels. So I'm going to explain this in 1D, but this explanation is generic to other dimensions. So let's imagine that we have a 1D chain where the atoms are separated by a distance d. I'm going to consider this chain to be infinite. So I can now look at the decay rates of this chain in momentum space. Okay, so I'm going to diagonalize this matrix in terms of block waves. And I'm going to plot these decay rates versus wave vector in the first Brillouin zone. So the Brillouin zone is bounded by pi over the distance between the atoms. And when I do that, I see that there are rates that are 0 and some rates that are different from 0. So the rates that are different from 0 correspond to radiative decay channels. And they all occur within the light cone, which is basically bounded by the maximum momentum that a photon of frequency omega 0 can have in free space, which is k0, which is omega 0 over c. And this is because in free space, a photon with a fixed frequency cannot have an arbitrary wave vector because of this relation between wave vector and frequency. And so as soon as you cross this light cone, on the other side, you go to excitations that have a very long momentum in the longitudinal direction. And this means that these excitations cannot decay into free space. So this is exactly the same as in an optical fiber, why light does not escape into free space is because the refractive index is providing an extra momentum in 1D. Therefore, there is some energy momentum mismatch between the photons in the fiber and the photons in free space. Here, this momentum mismatch occurs because of interference. So these are dark states and they are protected from decay. And so this behavior of having bright states and dark states, it's true, usually below certain distances. So in 1D, these dark states only occur below 0.5 lambda, and that changes depending on the dimension, okay? And again, if you have atoms where they are really, really separated from each other, then all these decay rates should be flat, and they should all be of the order of gamma 0. Okay, so then if you now have, instead of an excitation in an infinite system, if you have a finite system, this will probe this effectively dispersion relation, and there will be, like, this is, I think, for, let me see, 6, I think it's like for 11 atoms. So there will be 11 modes. Some of them will be bright and some of them will be dark. Okay, so maybe for the sake of time, I can skip these extra slides. I can come back to them. This is just, and again, another picture of why competition matters, and I'm happy to discuss it later if any of you is interested. Okay, so if we go now and we apply the notion of critical distance and the variance to chains of different dimensionality, here are the results. So this is what happens for a 1D chain. So here is the critical distance correctly normalized versus atom number. And these are numerical results in crosses and analytical results in this dashed line. And you see that this critical distance saturates at around 0.3 lambda, which means that atoms, 1D arrays of atoms, will only display superradiance where the lattice constant is below 0.3 lambda. If you separate the atoms more, you will never see a burst. And if you recall, I told you before that in 1D, there are only dark states that are produced because of destructive interference. below 0.5 lambda. So the reason why we are maximizing the variance here is because of destructive interference. So in 1D, Dickey superradiance occurs because of destructive interference, because there are dark states. So the way of maximizing the variance is to switch off some of the channels. And this produces this saturation of the critical distance with atom number. If you go to 2D and 3D, the physics is very different. So if you look at the critical distance versus atom number, in 2D, it scales sublogarithmically with atom number, and in 3D, it scales as a power law with atom number, which means that the critical distance at which you could observe a superradiant burst could be larger than a wavelength, and in particular, larger than the distance below which there are dark states, which means that the main driver of Dickey superradiance in 2D and 3D is not destructive interference like in 1D, it is constructive interference. And so in some sense, this is very, like it resembles very much what happens in statistical mechanics and in the theory of phase transitions, where you have a lower critical dimension, in this case is 2D, below which there is no phase transition because fluctuations kill long range order, and above which in 3D, for instance, you have enough neighbors to sustain long range order. So Dickey superradiance is a transient phenomenon. There is no notion of phase, but in 2D and 3D, the arrays have enough neighbors to have so much and so strong constructive interference that it gives rise to Dickey superradiance even for very separated atoms. And in 1D, if we wouldn't have destructive interference, Dickey superradiance should not exist. But because we have destructive interference, it exists. So in 1D, it's kind of a pathological behavior. And so this is the summary for our understanding of this many-body decay, or at least the early onset of many-body decay in arrays of different dimensionality. And so I mentioned before that my atoms for me are toy models where we have just like one excited state and one ground state. But I was visiting Urbana-Champaign recently and talking to Jake Covey. And he was like, well, what if we want to look at this physics in order arrays with in lattices or optical tweezers, you know, we should look at atoms such as ytterbium that have a very long wavelength transition. So this is a almost 1.4 micron transition, because in the end, Dickey superradiance, again, in 2D, for instance, this critical distance grows, right? But it's still not enormous, right? We cannot separate the atoms 1 kilometer. So we still need to be below a wavelength, at least for realistic atom numbers. So he proposed to look into ytterbium because it has these very long wavelength transitions, but on the other hand, these are from very highly excited states that have that decay to multiple middle states that then decay to the ground state. And so we were concerned whether, you know, realistic atoms would show Dickey superradiance even if they have very complicated internal structure. And the answer is that indeed they do. So this is a complicated plot to explain, but basically there are superradiant regions at distances that are below 0.6 lambda, and then there is another region around 1 and another region around 1.1. So again, in principle, you should be able as an experimentalist to see Dickey superradiance in atoms of complex internal structure. And the interesting thing is that you should see it, then lose it, and then see it again. So the behavior is very non-trivial. And the last thing that I wanted to mention is that this work can be extended on atoms in free space. And we have started to look at other type of systems, so superconducting qubits coupled to a transmission line. So here we have just a one-dimensional channel. The qubits can decay into the waveguide at a rate gamma 1D. And there is some other parasitic and local decay that is non-collective at a rate that is gamma prime. So in a 1D wire or transmission line, the field never decays. It's always basically, it mediates infinitely long range interactions between qubits. And these coupling coefficients go as basically cosines of the photon wave vector and the separation between the qubits. And so this means that the number of jump operators is very different from free space. There are only 2 jump operators here, in contrast to the n in free space. And this is because the photon can only be emitted to the left or to the right. So effectively, our jump operators are left plus right and left minus right. So taking the thermodynamic limit in qubit number is not the same as taking the thermodynamic limit in decay channel number in a 1D constraint geometry. And so if you look at the 2 decay rates versus distance, the first thing that happens is that there is a periodicity because of this like cosine-like interaction. And the second is that there are specific distances where the relative phase between qubits is n pi, where we go back to the decay limit, where we only have 1 jump operator that is bright and the other is dark. So we should clearly have superradiance there. And in between, we have like these points where there is competition, very maximal competition between the 2 operators. If we look at the numerics, so again, we did this for 16 qubits, you see that this separation of pi leads to the maximum decay superradiance. But for 16 qubits, no matter what is, and the parameters that we chose for gamma 1D and gamma prime, no matter what is the relative phase, we always have superradiance. The Hamiltonian, again, doesn't seem to be doing much. Only at very late times, it plays its magic, and I can talk about why this is the case. So this is very similar to free space. And now we can also take all our theoretical machinery and find an analytical condition for superradiance for qubits coupled to 1D reservoir that is that. And so we can do this for order and disorder arrays. So if you are in the superconducting qubit business, you may be more interested in somewhat ordered systems, but if you are interested in placing thousands of atoms close to a nanofiber, then it's a disordered system and the parameters are different. And so we have also a condition for you as well. And so another interesting thing that I'm not showing here, but I think is pretty fascinating, is that we can look at the photon emission rate, but that's only one observable. But in the end, like decay superradiance is a process of an avalanche. So you may imagine that the first photon is emitted in a random direction, either left or right, but then this fluctuation gets amplified. So you could start thinking about what is the statistics of the imbalance between emitting towards the left or emitting towards the right. And so if this would not be an avalanche, you should see some normal distribution centered at 0. But in reality, what you see, at least in particular distances, is very separate peaks where you actually have this notion of, once the system decides to emit in one direction, then, it always is that direction. So there is some notion of a spontaneous symmetry breaking, but in time, or basically an amplification process. Okay, so with this, I want to finish. So I really think that atomic arrays are an interesting platform for studying many-body physics, in particular of the merge of many-body physics and quantum optics. And it has interesting applications for quantum information science and metrology. And so we have started to understand the many-body decay in extended systems, but we have also ideas to pursue in the future. So one thing that I find particularly compelling is to start driving this system incoherently. And so there we can actually establish a steady state, and therefore we can make more proper connections with the notion of phase transitions. We may also be able to, even though we're driving the system incoherently, the decay produces correlations between the atoms. So we may have a source of coherent photons in the array, even if they are not in a cavity. Another thing that is interesting is that once you realize that most of the dynamics is dissipative, you may find new ideas for solving dissipative evolution and finding computational techniques that are appropriate for this problem. So it's something that we also started looking into. Today, I've looked mostly or described our work on decay superradiance and rapid emission of photons, but I'm really, really interested in the opposite phenomenon, which is the preparation of subradiant states. These are dark states that do not decay because of destructive interference. And so these states are usually very hard to prepare coherently precisely because they don't talk to light. So just by sending light to the system, you won't prepare a dark state. And so one option is to actually decay into them. So once we start understanding this dissipative evolution, we would like to use it and perhaps via measurement and feedback techniques, guide it into the preparation of interesting states. The fact that we have an enhanced photon emission rate at distances that are non-negligible makes me wonder about whether this could play a role in dissipation in river arrays for quantum computing. And some other problems that we have started to look into is disordered systems and also quantum optics of condensed phases. So going from array to disorder to truly condensed system. And with this, I wanted to acknowledge my group, and in particular, the people that have been working on this problem and leading this problem, which are all absolutely fantastic. My postdoc is Stuart Mason, my student Eric Sierra, and my other student Silvia Cardenas Lopez. If you're interested, you can read our work, which is these 3 publications here. And I should also mention that there is a paper by Francis Robichaud that is pretty awesome, that took our technique and extended it to directional superradiance. So here we are integrating over all space, but you can adapt this technique to ask yourself, well, will I have a burst in this specific direction? And then if you want to look at superradiance, not just like early times or the insight of why superradiance happens, but you're interested in like what is the height of the burst, where does it happen? You may need to use other methods, and some of them are included in the work of the group of Susan Yelin. And so with this, I'm looking forward to any questions. Yeah, and thank you so much.
Thank you so much, Anna. It was a wonderful talk, very clear and inspiring. And maybe I'll actually abuse my power to ask one question myself right away. So you mentioned disorder. And of course, if you think about superconducting qubits as artificial atoms, they're unlike atoms in that not a single qubit is like the other. So how much disorder is acceptable if I want to observe some of the physics that you described?
Yeah, that's a great question. So I have some slides which may answer that. So let me see if I find them. Is this a good one? Yeah, this might be a good one. So the good thing of superradiance, honestly, is like it's been observed in so many systems because it's actually robust, because it's effectively a broadening of the line width. So one thing that we did is to look at exact dynamics of systems that are imperfect. So we looked at imperfect position, but you are asking about superconducting qubits. So I'm going to talk about imperfection in terms of non-radiative decay rates, and also imperfection in terms of inhomogeneous broadening, so different frequencies. So the first part is here. So this is for 16 atoms. So it's not a very large system, but you see, so this is the perfect situation. So this little gamma is the non-radiative decay rate. And so you can make your non-radiative decay rate of the order of the radiative decay rate, and you still have superradiance. And eventually, if you keep increasing it, it will disappear, because then again, the qubits are emitting independently from each other. But if you increase there will be always like a large enough atom number where you overcome this problem, at least in large dimensions. This is not true in 1D in free space, but it will be true in 1D in 1D channel, okay? And then this other plot is for inhomogeneous broadening. So here we are considering that each qubit has a frequency that is identical from each other, but then it has a dispersion, like a Gaussian dispersion of some standard deviation sigma. And so again, if you have like sigma of 10, you still have a burst. It's just reduced in size. So again, you can overcome these problems by packing emitters, but I know also in superconducting qubits it's really hard to go beyond like 10 and things like that. So I would say it depends. It depends on the system, but I'm not super pessimistic. Whereas there is other physics like, I don't know, subradiance or dark states. These are hypersensitive to imperfections. Superradiance is much less insensitive. No, it's more insensitive. Yeah, it's like double negation. Yeah.
Great, thank you. Questions from the audience, please. Zoom silence at its best, please. Nathan, you're still muted. Okay.
Yes, thank you. I have a question. I'm wondering, I guess I'm wondering about kind of the algorithms or the techniques you use to study these arrangements, because in our studies at Howard University in Washington, studying superradiance, we've been able to use a number of approximations to go to much larger systems using coherent green function techniques, where we don't consider, I think, the level of detail that you consider, but we are only working in the single excitation regime. So like the single photon limit.
Yeah.
And I guess I'm wondering, because we've looked at, and for our studies, we want to know more about the multi-photon limit so we can look at these avalanche effects. That basically what I'd say is I was just enthralled through your talk about the study of, you know, the details and the geometric effects in the multi-photon limit, because we don't hardly know anything about it at all. And I guess, I don't know, I guess, but my question really is if you can suggest sort of the order of approximation to go with. We have a Green's function Hamiltonian with a non-Hermitian term added onto it to study the superradiance. So we haven't even used a Lindblad formalism, and I think that's why we've been able to get away with it. Do you know, is there anything kind of in between?
Yeah, I think that's a great question. So when you look at single excitation superradiance, so basically it's like you prepare some coherent superposition that just decays faster. So you won't see the burst, but you will see an accelerated rate. Like, so instead of gamma 0, it will go as a factor of n times gamma 0. So if you do that, again, the complexity goes as n in the linear excitation domain. So, you know, you can deal with 10 to the 6 atoms and, you know, you can be fine. As you plug, like you put more excited, and the non-Hermitian Hamiltonian is great because there the jumps are kind of like the final state of a jump is all atoms are in the ground state when you only have one excitation, so it's trivial. So you don't need to keep track of the jump. So already the non-Hermitian Hamiltonian is good enough. You don't need the density matrix for anything.
Exactly.
Well, unless you want to track like but exactly when it happens. But yeah, overall you don't need it. Yeah. So that's completely the opposite case where you go to more and more excitations. So one thing that our method does very well is, I think it provides insight. On the other hand, it doesn't tell you anything about the size of the burst. As if you want to find the size of the burst, there are other techniques. So I know the work of Susan Yellin, but one thing that we have been trying is accumulant expansion. So basically you have expectation values of different number of coherent operators and you truncate. So you say, well, effectively, I'm going to have like, you know, sigma, 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 sigma. And then if I have 4 of these, I'm going to decompose it in 2 of sigma, 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 sigma. So you kill like correlations, and you can do this to one, like the 0th order is mean field, or like 1st order is mean field, 2nd order is like 2nd order cumulant, 3rd order cumulant.
Right.
So
is this like a truncated Magnus expansion then? Is that what you mean in terms of the commutators?
I guess, but honestly, I don't know that language, so I cannot.
Okay. No, I understand. I understand. If you could recommend a reference.
Yeah, I can send you some reference. So the problem is that it's uncontrolled. Like you don't know if it's working or not unless you do the higher order, and then if it converges, then it's good news. So I can tell you, we have looked at that like 2nd order with 16 atoms in a chain, and it does work pretty well. What it captures superradiance like the early times, the burst, but it doesn't capture at all subradiance. So like you would go up and then the photon emission rate slows down because you're populating a lot of dark states. And in these dark states, there are a lot of correlations that are built up over time. And this completely explodes any type of cumulant method. But the peak seems to be well captured. So we have done that for 2D as well. And we are testing it. So this is the best that I can tell you right now. So what I would do, and actually what we are doing now, is to develop the cumulant techniques because we want to tell experimentalists like, okay, this is what you should see, you know, within 10% error. So this is what I would do, and this is what we're doing. And I can send you a reference.
Yeah, perfect. Perfect. I'll email you. Thank you.
Eleanor, did you have a question?
Yes, thank you very much. It was a really interesting talk, and I don't come really at all from this direction, but and maybe this is a bit innocent, and I also missed a couple of minutes because someone came in, but maybe you mentioned this, but so for example, a superconducting array of qubits or kind of any quantum computer that you have, if you are looking at your qubit in terms of like an excited state and a ground state, you know, basically one of the massive processes will also be this kind of photon lossless decay. So are you basically saying that if you have a quantum computer setup, then you're better to take away any qubits which are likely to decay fast? So any qubits which have very bad kind of coherence properties, they actually really ruin the properties of all of the other qubits in the array as well. So you're better to actually remove it completely rather than leave it in, because if it decays, it will kind of cause emission.
I mean, for us, like all this physics happens no matter what's the decay. So actually all of them have exactly the same decay rate. It's just that as soon as they share some common path, this problem is going to happen if you have many excitations. So if you're actually thinking of a quantum computing architecture, there might be many things that save you, honestly. One thing is that maybe you only have 2 qubits excited at one time, not all of them, so that's good. The second thing is that if you're doing this not with a transmission line, but you're doing it in free space, then because of this like range of interactions, then you might be in a place where, you know, the rate is not enhanced very much. So there are ways of why, you know, you might not be dead from this. I would be So I cannot claim that, you know, this is going to kill quantum computers, because I think there are, you know, other reasons that are more, you know, that make quantum computing more difficult than this. But I'm saying that it is not clear to me, whether in particular for like arrays of atoms in free space for quantum computing, whether this is going to play a role or not. Because in this Rydberg, with these Rydberg atoms, they have levels that are really close in frequency, so the wavelength is microns, and so or longer. So then effectively the atoms are very close to each other, even if they are separated 3 microns apart. And so maybe, you know, this can play some role. I'm not sure. We don't know. That's the answer. But I don't think it's about taking some out. Like I mean,
even if there's one which had bad like coherence.
No, I don't think so. So actually, if one kind of decays faster, I think actually I don't know what would happen. That's a good point. I don't know. I would say, I cannot comment on this. I never thought about it, like to make it. I thought about all other possibilities, I think, except like some of them decaying faster than the others. The interactions would change, but I don't know if it would be much better or much worse. Yeah.
Okay. Yeah, but it was really great. Thank you so much. That's great talk.
Thank you.
All right. I think we have time for one more question. Anybody?
I have one about applications if there's no one else.
Sure.
Go ahead.
So my question is regarding, I think you mentioned transmission during the last question. And so I'm wondering if you've thought about things like a super radiant laser. In our studies, we're looking way in the bad cavity limit because we're interested in biology. So what I want to know is what you understand about things like coherent transfer, exciton transfer, say for communication or information technologies. What kind of improved information transfer rates would you be able to imagine from your studies and your systems?
I can tell you what I think about lasers in this system, which is something that I'm really interested in understanding better. So I think I understand a regular laser that operates in a high Q cavity limit, where the photons are there. Like you have this macroscopic occupation of a bosonic mode that forces the atoms to emit into it, and that kind of creates the coherence in the laser. The bad cavity laser doesn't work like that. And so then I started wondering, why do you need the cavity to begin with? And it's basically to provide an optical mode, so some direction of emission. And so in the case of arrays, you may consider, and this, honestly, I'm speculating here, I'm not sure if this is true. Like if you incoherently pump, this incoherent pumping, if it's very strong, it will destroy all type of correlations. On the other hand, decay produces correlations, and also in a 2D array, you may have directional decay, right? So then there might be an optimal point of distance that is constant and pumping that creates like a coherent source of light. And then it's like directionalities, yeah. And
That's
that
just
would be
what I wanted to hear.
yeah, I think so. I mean, honestly, I go and I talk to people about this, and some people are like, yeah, for sure, and then some people are like, no way. So I think I'm leaning towards yes, but this actually I have a student that started to look into this. So I will keep you posted. This is with respect to things like lacing. With respect to things like information, I think more in terms of storage of information, and for like things like storing information, you should not rely on super radiant states. You should rely on dark states. And so, but eventually you may think of, well, you know, you can store something and then release it really quickly, perhaps via coupling to some super radiant states. Although I don't think Dickey super radiance is the right way to go there, because you start from an initially like incoherent state where there is no information. It's just a product state. So I would say generically these ideas of an array, like it allows you to switch between dark and bright. I think that's really cool with respect to storing and releasing information. Dickey superradiance, on the other hand, I don't think it's like the good way to go about, you know, making a memory or like releasing photons that carry some sort of information. But it's true also that through decay, you have correlations that are imprinted in the atoms, and then you can I don't think this is like information that you care about, like you haven't stored, but you have information about the system and the many body dynamics of the atoms. If you measure the photons in the right way, like different directions and different times and so on, you will see correlations that are non-trivial. Yeah, I don't know. I think I talked a lot, but I don't know if I answered your question.
It's very helpful.
Thank you.
The key thing I took was the issue with in our system, we basically have no cavity in the sense of quantum optics where you have mirrors and things. So the geometry plus pumping, if that's really all you need, that's what I want. That's what I need. That's what I have.
Yeah, I mean, I think that might be the case. And I think it really helps the fact that you have order, because if not, you have like these atoms that might be like randomly close to each other, and this may lead to defacing. So that's a problem if you want to see like this burst and to have coherence in your system. So and then with respect to what makes it different from cavity also is the fact that, you know, you may for different, so if you do this in the infrared, maybe this is not an issue, or at optical frequencies, but there are frequencies where you don't have, you know, it's not possible to build good mirrors, right? And so maybe you don't need them. So that is what I would say, the perspective of application.
Perfect.
But
thank you.
To be determined, I cannot really say.
All right, unless there's another urgent question, then let us all thank Anna one more time. Thank you so much for being here and giving this wonderful talk. I really enjoyed it. I learned a lot. Thank you everyone for joining. Again, I believe this is the last talk for the academic year, so I wish everybody a wonderful summer, and see you again in the fall.
Bye. Thank you, Jens.
Thank you, Anne.
Bye.
Bye. Thank you.